Welcome, everyone. So we're going through the Understanding Deep Learning book. This is the author's slides that are available on from the book site. We'll use this as a template for discussing the chapter. I just want to mention, our intent is for this to be um, more of an open discussion. So if you have questions about anything, I invite you to stop, interrupt, use the chat, raise your hand, whatever, ask questions. But then also, if you have experience and can add any color, feel free to also chime in. Um, I've made some like wildly bad predictions about how long a meetup will take, but I really do think this material doesn't have to take that long, and that we have room for discussion this week. All right. So with that said, we've spent the last few weeks, we're talking about this machine learning pipeline. It's mostly talking about supervised learning. This will be the last chapter in this part of the book. Next week, we're going to start talking about architectures. So we're going to get into CNNs and then transformers and stuff like that. So 4 chapters on that. And then after that, if you guys remember, we get into generative models and unsupervised learning. So we've talked about gradient descent and things like that, and so one of the questions is why is there a generalization gap between the metrics we see on our training set and our held out test data? And so one of the most common reasons is because we end up overfitting on the training data. So we're going to talk about today, it's all about regularization. And I'm not really familiar. I assume the author knows way more than me, but says that the roots of the term regularization, technically, it just means specifically the old ways people did regularization, where they add an extra term to the loss function. So if you remember your linear regression, you can add an L2 loss to that, and you have ridge regression. You can add an L1 loss to that.
Well, it is historical roots.
Yeah. So he says technically that's the history. That's what maybe at some point the dictionary definition of regularization was. But we're going to use the term the way most people use it these days, which is much more broadly. Okay, which is just techniques to address this overfitting problem, this generalization gap problem. All right, so here's an outline of what we're going to go through, a couple different topics. Okay, first we're just going to talk about our historical roots, explicit regularization by adding something to the loss function. So here's our standard loss function. And basically, let's say we have some parameters, phi. We're going to find the parameters that minimize our loss function. And what is our loss function? Our loss function is just the sum of the losses on each example in our training set. All right. So we can modify this. We can do regularization. And so in addition to just the sum of our losses, it's the sum of our loss plus we're going to add a penalty. And this penalty function we're just going to call G. But G is something that is lower for parameters you like and is higher for parameters you dislike. And so the standard thing is G is going to be higher for bigger parameters. So the parameters we like are going to be the smaller ones. And I believe we have a slide coming up, but I'll say a little bit extra about that. Yes, so it's a penalty function for having bigger parameters. And then this lambda factor allows you to control how strong this penalty is. So you don't have to change your G function, you can just change your lambda. If you make lambda smaller, if you make lambda 0.0001, then it's almost as if you had no regularization. And if you make lambda 1,000,000, then it's going to swamp your regular loss and probably a terrible idea, but basically your model's just going to give you whatever parameters meet the lowest G and kind of ignore your training data. So here's an example. Previously, we saw there was this, I don't remember what he called it, there was this funky function. I think it had some signs and some e to the x's or whatever. And if you use matplotlib and you plot it out, then basically you see this sort of not not overly simple, not obvious loss landscape. Okay, so the darker areas are lower loss, and so you can see there's sort of a local minimum on the left here. There's a local minimum in the upper right. I believe this is the global minimum from earlier chapters. And then you've got some other areas, and these are either like very small local minima or possibly saddle points or whatever. I think this looks like a small local minimum, this one. These are not very good local minima. And so the idea is, can comport function, yeah, I think that's, sorry, I think that's what it was called. Can we add some regularization? So if we have regularization that says we want small parameters, and this is only 2 parameters, right? So on our x-axis, we have the first parameter, y0, and the y-axis, we have our second parameter, y1. And so when they're both 0, if you look at the axes closely, I don't know, this 0 is definitely here in the middle on the x-axis. It doesn't actually look like it's in the middle on the y-axis. But anyway, the idea is you have, again, dark means smaller value. So if this is your regularization term, maybe this is not like any particular, this may not be standard L2 loss. This may just be like, imagine that you have some regularization function G that just looks like this bullseye. Then what that's going to mean is it's going to favor parameters that are near this center point, and it's going to slightly disfavor points that are farther away. Now, just because it favors points near the center doesn't mean that the final place where the model converges has to be exactly here, right? If you have a very deep valley and it's further away from the center, it can still have smaller total loss when you sum these two. So what does it look like when you sum these two? Well, then you get sort of this picture on the left gets modified because now it's favoring here in the center, and these ones are a little bit less dark because they're further away from the center. And then these ones over here are pretty much like practically wiped out because the increasing loss from the regularization term kind of overran this very, very shallow minimum down here. So pictorially, this is what we're talking about. We're saying when we add some term, theoretically, you could use matplotlib and you could just map out what that loss landscape looks like for just that term, independent of the actual training data and the model that you're trying to train. So does that make sense? Any questions about that? All right, let me just take a peek at the next slide. All right, yeah, so before we get into that, I think in the chapter, the author just has like a quick sentence or two talking about like why smaller parameters are better. But I thought maybe if we just talked about like an explicit example, you know, so usually when I look for like simple examples, I often just go back to like predicting house prices or whatever, right? So if you had a neural network and you're predicting the price of a house, what could happen is that ultimately what you want is you want 3 times the number of bedrooms to be one of the things that's in your house calculation. But if you've got a network that's wide enough, you could easily have one node that does, say, 13 times the number of bedrooms and another node that does negative 10 times the number of bedrooms, and then you just sum those two later on in your model. Okay, and then the net effect is still going to be 3 times the number of bedrooms. But of course, if anything slightly happens that causes this to not work exactly right, you've now got this really, really large value of 13 and 10. So mathematically speaking, you could also have 1003 and negative 1000. Or you could have 1 billion in 3 and negative 1 billion, and the two still technically cancel out, but you can just see that anything that destabilizes this system is going to cause like real problems. So another example I thought of is, let's say you had two inputs, and one was a student's age and the other was the student's grade level. Okay. In the United States, like in September, most people it's like 5. So like you're 6 years old when you enter first grade. And so if you did like 1,000,000 times their grade, um, uh, and then you did like 1,000,000 times their age minus 5, yeah, most of the time those two would completely, or negative 1,000,000, those two would completely cancel out. But in the few cases where you have one kid who it's not a 5-year difference because, you know, they started school early, they started school late, they skipped a year or whatever, instead of those two exactly canceling out, now you're going to have a factor of 1,000,000 difference between those two. So that's the reason why basically the larger parameters you have, it's stuff like that, where the larger your parameters are, um, uh, even though things may cancel out when things work perfectly, you're potentially introducing really large variation into your system. So any comments, any questions about like why, generally speaking, smaller parameters are sort of like simpler, smoother, I guess for like real world problems, like the smallest parameters that work are generally speaking the ones that you prefer. All right, so moving on. I don't think this is super important, but there's this linkage that you can make. So um, maximum likelihood says, hey, if we just take the maximum probability of our y's that we're trying to predict, our labels, you know, based on our input data, then we're, you know, finding the maximum theta. Okay. If you change this to a conditional probability with a prior and you apply Bayes' rule, you can kind of work through the math. Okay. And what you will see that is this probabilistic interpretation can also be rewritten. Okay. And it's not shown on the slides here, but basically, basically you do the log probability, and what you'll see is you end up with just sort of like your regular term and then a sum here. And so the idea is that when you're adding something here, you can interpret this as if you think in terms of Bayes' rule, you can think of this as basically just adding some extra term which is based on your prior assumptions. And so in this case, a simple way of saying it is when we favor small parameters, our prior is that we're again, that we're favoring small parameters, that we think that small parameters are more reasonable for this problem. So we're not saying that we are good with all parameters on the real number line from negative infinity to positive infinity equally. No, what we're doing is we're saying that our prior assumption is that our parameters are going to be closer to 0, and they're not going to be 100 or a million or a billion. There's a question in the chat. I don't think that this really addresses the exploding gradient problem. I'll just stop there. If we have time at the end, maybe we'll get into a little bit more. But this is really about changing the local minimum that your function is gonna, that your neural network is gonna find. Okay, so if you follow that, that can give you a little bit more intuition. I don't think that's super critical. So now we introduce explicitly. What kinds of regularization do people do? The most common one is historically L2 regularization. So you basically take each of your parameters, you square them, and you sum it up. And so this is going to penalize you for any large parameters, and it's going to penalize you in particular for any single super large parameters. So for example, if you had 10 parameters that were each 2, the penalty won't be that bad because 2 squared is 4. But if you had a whole bunch of really small ones close to 0 and one parameter that was 20, even though they all sum to the same thing, 10 parameters 2 is 20, one parameter 20, but 20 squared is going to be 400. So what this is really doing is saying, I don't want any big ones. I'd rather have a whole bunch of smaller ones. So one of the questions is, why does L2 regularization help? Okay. And the idea is that without regularization, your model gets 0 loss if it is able to exactly hit each of your training points. And sometimes it's not possible to exactly hit it, but still, this idea of slavish adherence. No matter how wacky my function looks, I'm going to just modify it until I get as close as possible, hopefully exactly hitting each point. And by having this penalty term, it's basically saying that, hey, you should get close, but if you're having to do something really crazy, like, have this funky polynomial that has these really large terms, in order to hit those points, I'm going to say, don't go nuts on that. Okay, what's the closest you can get with reasonable small looking parameters, which hopefully will give us a sort of a smooth function. The assumption here is that if you have nearby data points, that you would expect the function to interpolate very smoothly, perhaps close to linearly between those two data points. This gets a little bit funky in super high dimensions, but in low dimensions, it certainly sort of makes sense that if you have a house price prediction and you have a house that has one bathroom and it's $100,000, and you have a house with 3 bathrooms, everything else is the same, and it's $150,000. You don't expect the 2-bedroom house to be some crazy number. You expect it to be somewhere pretty much sitting between the $100,000 and the $150,000 prediction. That's not like always true, but like in most problems, that's sort of like the prior that we kind of want to impose on the system. So there's a question in the chat. In the gradient descent optimization, do we need to optimize the lambda, or how does the gradient descent process work with the regularization term in the cost function? So unfortunately, yeah, lambda becomes another hyperparameter, and there's no way to know what's a good lambda. Okay. If you kind of know the size of your data, so like let's say your data is all scaled to be mean 0, variance 1, we can say right off the bat, it's extremely unlikely that a lambda of like 1 or 2 or something big like that is going to be appropriate. But should it be 0.1? Should it be 0.2? Should it be 0.05? Unfortunately, that's something that just falls into that standard hyperparameter optimization business. So if you look at people who are doing, we'll get to it later in the chapter, like weight decay on a large language model, there is no way to know the right amount. You just have a validation set and you train it with one value and you see what the results are. And then you train it with another value and you see if it's better or worse, and you mess around with it like that. I would say that somebody tell me if you have any practical experience otherwise, but at least the strength of regularization is usually like convex. Like there may be a good spot, and it gets worse if you get too big, and it gets worse if you get too small. But it's usually not something super wiggly where it's like you have to do a very exhaustive search of lots of values. Usually, it's just like, yeah, I made it smaller, and my model kept getting better, and then at some point, I started getting even smaller, and my model started getting worse, and so I just stopped at the. Is that any other comments? Anybody else have a different experience with? All right, yeah. So here we go. Avoiding slavish adherence, smoothness between the data points. Here's a pictorial example. Doesn't really say exactly what the neural network is, but that's not super important. So you train the neural network vanilla, and you'll see that it's hitting every data point exactly. But so it's kind of this really jaggy function that goes through all the data points. If you add a little bit of regularization, this is L2, doesn't really change much. So we got to make it a little bit stronger. And now you'll see in a couple places, like over here, it's kind of missing the data point in order to be smoother. Again, the intuition is that um, um, smaller parameters will cause it to be smoother. It's not like in theory 100% guaranteed, but that's the general gist of it. So you might think that this 0.001 lambda is looking pretty good because it's pretty close to the black line, and some of these points that are farther away from the black line, the model's actual predictions in this light blue um, seem to be moving away from those data points. And then what you can see is that if you keep cranking up your regularization, you're forcing the function to be flatter and flatter. And then I would argue that at 0.1, it's already too strong. If we cranked it up even more, you would see that this thing would get even flatter. It would start to ignore the data points. So um, that's kind of what L2 regularization looks like. All right. The next topic is implicit regularization. This is actually relatively new. I was looking at the reference papers, and I think they were like 2021, 2022. But the idea is that when you do gradient descent, the idea is that um, you're following the gradient of the loss curve. Sorry, I keep clicking accidentally. So in this case, imagine this darker blue line is the true gradient of your loss function, okay? But we're not doing the calculus thing where we're taking infinitesimal steps. We're actually doing a batch, and we're taking, you know, uh, certain size steps, based on our learning rate. And so the idea is imagine these discrete steps in the light blue arrows. It doesn't exactly match this dark blue line. Okay. Um, and so ultimately, what you can show is what is this difference? If I were to get a closed form formula for the difference between the dark blue and the light blue, what would that look like? And so then this is where you see gradient descent. You have this term which is the square of the gradient. So because the square is always a positive value, then basically this term is bigger uh, the larger the absolute value for gradient. So large gradient means steep slope. So that means that this loss function is penalizing you in regions near steep slopes. So you want two things. You want to find a local minimum that has a wide basin. You don't want it to be just a single local minimum at the bottom of a very narrow uh, uh, valley with very steep walls. But it also means that you're slightly disfavoring, even when you're just wandering around before you get to the minimum, you're sort of staying away from steep areas. You're not going to completely avoid them because this term isn't necessarily going to completely, dominate and overwhelm your regular loss. But it means that you're going to slightly disfavor places that are steep. And I think that the intuition here is that when you have a true like uh, relatively close to global optimum, it's going to be a fairly wide basin that you're descending into. And you may just have little fluky things where you have a certain data point, and if you set your parameter a certain way, you can nail it right on that data point. And you'll just have like this kind of small, tiny little sharp depression in your loss landscape. So that's basically the idea. Is that, hey, we want to follow the broad contour, not worry about every single little pit and nook and cranny. Um, and so this corresponds to a term that says avoid sharp places. And if it's a true big basin that just happens to have one sharp side, then it might mean that instead of you going straight down it, maybe you kind of wander around into the basin, kind of take a slightly longer route, but that's still okay because you're still, it increases your training time slightly, but it means you still get to the bottom of the big basin. This is full batch gradient descent, which like nobody does. And then you can see SGD has a similar term where basically they say the average difference between the gradient of your batch versus the true gradient, and you square that. So once again, this is always positive. Once again, this means that you are going to sort of tend to avoid steep areas, but it also means that small batches are going to have larger differences just due to small sample size. And so if you want your SGD to kind of like wander around more, then small batches may actually help you. So they say larger learning rates for full batch, and then smaller batches for SGD if you have like a tough problem. This by the way, this does not necessarily that you can mean that you converge faster. It doesn't necessarily help your training time. What they're saying is that it will improve the your model's predictions when it finally converges. Okay, so just know that adding regularization does not necessarily speed up. Generally, will do the opposite. It'll slow down your training with all the techniques we talk about. Question in the chat just about this notation. So basically, the double bars here. This is a norm. So this term, the loss with respect to your parameters, is not a scalar. So if you have 100 parameters, this is a vector of length 100, and so this is why we need the norm terms, and we can't just like do a simple squared, but it's basically the same concept. All right, here's another picture showing your original loss. It's hard to tell, but basically the idea here is the light areas are penalizing steep slopes, and the dark areas are favoring places where the slope is relatively flat. And so if you combine things, then you get something that looks like this. And once again, what we're hoping to do is to favor our really big basin and disfavor any small little local minimum. We don't want to get stuck in this. All right, here's a chart showing MNIST with label noise, and I think the one on the right is a little bit easier to read off. You can see that this dark gray line is the smaller batch, the brown is the medium-sized batch, and the light blue is the full batch on their training set. And so you get best performance with the smaller batch. That's the thing that we said before, is that smaller batches work better for SGD. Okay, so that kind of covers the formal stuff on old-fashioned original regularization, where you add a penalty term, and then why is it that gradient descent on neural networks seems to work well with implicit regularization. Now what we're going to talk about is a bunch of different techniques people use that are not the old-fashioned dictionary definition of regularization. We're not adding a penalty term in most of these. Instead, we're just doing a certain technique. And so these are the things that people have found. One thing that the book doesn't really talk about is like, well, when do you use each one? So maybe we'll talk about that a little bit. But some of these, it's really going to show up in your problem setup. And then in other cases, it's like after we've got the problem set up, we can do things like we're doing images. We'll do things like add flips of the images or slight rotations or adding slight noise, things like that. All right, so first technique, early stopping. Intuition described here is that we initialize the neural network with relatively small weights, and the longer you go, the more time they have to get really big and try to overfit, so that by stopping early, you will reduce model complexity. So a simple way to implement early stopping is every so often while you're training, you save off the weights and you watch as your validation loss goes down, down, down. And then at some point, if your validation loss starts going up, then we say, hey, maybe it's now in a regime where it's overfitting. So we go back to an earlier set of weights when the validation loss was really small. So one of the great things about doing this is you're only doing one training. So like there's that great question earlier about how do you know the right lambda? Well, you might have to do 5 training runs to find a good lambda for L2 regularization. This is just one. So pretty simple to implement. And if I remember right, this is just snapshots from training a very small model. So it starts out, of course, with random weights, and they're learning. They're not very close at all. You see it starts to get better and better and better. And then eventually, if you let it go long enough, whatever, 200,000 iterations, it's now starting to overfit. So the idea is that you can do early stopping somewhere like maybe image D. Okay, that was one technique. Ensembling's another technique. I don't think ensembling is all that popular because it's very expensive. Okay, so what you can do is you can train multiple models of different kinds, whatever they are. So they could be different training points on your current model. They could be whatever. But if you have 5 of them, then basically it's going to be 5 times the inference cost. And so it's really not that particularly popular. We do it in Kaggle competitions because as long as you fit under the compute budget imposed by the contest, you're willing to squeeze out that last 0.0001. But in the real world, I don't see a lot of ensembling of common model techniques. Obviously, you have things like random forest, gradient boosting trees, which are inherently called ensemble techniques, but I really don't see people very often saying, oh, I trained a neural network and I trained a support vector and I trained a random forest. And then I just said in production, we're going to run all 3 of those and average them. And that's how we're going to predict the housing price. So somebody else can share if they see
I
something
think
like
it's
that.
also called consortium learning. I read an article, so they were using this kind of approach that you just mentioned.
Mm-hmm. Okay. Question in the chat: Do we start with implicit regularization and then just add if it doesn't generalize well? Yeah, generally speaking, like again, some of these are going to show up in your model in your problem setup. So we're like talking about transfer learning, right? But if you have a model, then yeah, as with just about everything, like generally my advice is start simple and then you start layering on things. And so like regularization to see if it helps. So once again, we've got this little curve that we're trying to fit. And here's an example. I did not find this example to be very easy to understand, but basically what they're trying to say is that we have this model 1 and model 2, model 3, model 4. We're going to ensemble them, and that this blue line is supposed to be a little bit less spiky than the original model in the gray. So you can see a couple places where the original model deviated overfit, and the light blue's a little bit better. It's not perfect, but it's a little bit better. All right, next technique, dropout. This is pretty common with neural networks. Here's a pictorial example. Here on A, we have our full network, neural network. So each of these nodes is a ReLU node, so it's got like some sort of weight, and it's got a ReLU. That's why the little picture there. So if on one training batch you see that we dropped out these 2 nodes, okay, then they're effectively turned off. It's all zeros. but a different training batch, maybe we turn off these 3 nodes, so on and so forth. What's that going to do? Well, in the example that I gave where you had like one thing that says, take the number of bedrooms times 1,000,003, and another one that says, take the number of bedrooms times minus 1,000,000, yeah, they cancel out. But if you drop out the minus 1,000,000, now you're going to have a real problem because you're only going to be left with the times 1,000,003. And that's what we're showing here, is that you've got something that does like a plus and something else that does a minus. Notice there's no training points in this region, right? There's a point there, there's a point there. This is a one-dimensional example, so a situation like this is much, much more common in a high-dimensional data set, okay? So they're saying, imagine that you sort of drop out the node that's pulling it down, then you might wind up with a prediction that looks like this. You're going to have a super huge loss on this particular batch. And so as this happens just randomly on different batches, it's going to try to pull this down so that this circled area, instead of doing this in between your data points, it's going to pull it to something that's closer to a straight interpolation. And so they show that in figure C. They do 2,000 iterations with dropout, and what it's forcing it to do is to not have these large values that pull things up and down, but rather try and keep things as level as possible. I think that dropout was used fairly commonly in training LLMs in the early days. So like BERT, GPT-2, you know. I don't, I haven't seen it as much lately, and I don't know exactly the reasons. Sorry, I keep accidentally clicking. If it's because we've got like better normalization with the, you know, the layer norm and all this other stuff that we're doing. But for what it's worth, it seems like the models are a little more robust and they don't need this regularization. Once again, if you don't need it, it will train a little faster if you don't use dropout. Anybody else? Any comments on dropout?
I feel like dropout is particularly useful when you are data constrained, and that's probably why it's not as useful on
When
big
you're training on
LLMs.
2 trillion tokens?
Yeah, I think you might, if you train it infinitely long and you go over the data multiple more times, maybe dropout is useful, but when you're only seeing the data once, you're not getting anything out of not using the full capacity of your network.
Yeah. Thanks, Ryan. Theoretically, I think some people have tried stuff like trying dropout only in the earlier layers and not in the later layers, or only at a certain point near the end, in order to minimize. You want to get the best regularization you can, but at the minimum sort of destruction of your data, which then can either hurt model performance or just cause it to take longer to converge. Yeah. All right. Next topic, adding noise. Gosh. So there's different ways you can add noise. They show here an example in our 1D where you just add, so there's only one input. And so you just, in this case, they add Gaussian noise. So these little dots are supposed to mean that sometimes on a certain batch, the point is pulled to the right. On other times, let's use this one up top. Sometimes it's pulled to the right, other times it's slightly pulled to the left. And then this, you know, adds a bit of regularization to the model. And so you can see that the original model overfit, follows all these points very closely. And then this one with the noise smooths out a little bit. Don't think there's a slide. I can't remember, but if I remember right, there's no slide. For images, you know, it's very common to do augmentations, and some of them are lossless. So if you're doing classification like ImageNet, and you have a picture of a dog and you flip it left to right, mirror image, we consider that to be like non-destructive. That's still a dog, even though it's facing to the left instead of facing to the right. But we do other augmentations that are actually somewhat destructive. We noise the image, we do blur, we change the color scheme. Sometimes we even just cut holes in the picture, stuff like that. So that is much more like destructive noise versus just simple things like rotations and flips. I'll say a little bit about Bayesian approaches. So basically, instead of trying to find a point estimate for each of your parameters, you can find a probability distribution around each one. And if you do that, then and you combine all of those probability distributions, then you'll get a final probability distribution for your target variable, your y. So the more I learn about Bayesian approaches, they're very cool. They're principled. They seem to work better. But here's the catch, okay? Bayesian doesn't really work for neural networks, and it doesn't work for super large neural networks. So even though you can actually do variational approaches, you can do Markov chain Monte Carlo, MCMC, it's completely impractical. You would never do it for any realistic sized, even like, whatever, llama 7 billion or something. It's just completely computationally intractable. So I actually like the idea. And there's a picture here. Sorry, my mouse is acting up. That like here, you on the top row, you can do like point estimates, and you get these different predictions. With the Bayesian approach, you can, it's not really shown, but like imagine like there's this light blue line you can barely see, and there's like one standard deviation around it. And so you can sort of understand that even though the individual example data points are going to pull things, the Bayesian approach is going to much better understand sort of probabilistically what sort of a smooth curve in between all these data points looks like. And you have to have some priors and say, like, what kind of noise do I think there might be in data points? So if you ultimately have some prior that assumes there's no noise, the noise is super, super tiny, then this Bayesian approach basically turns back into your regular point estimate approach. But if you have a model that allows for certain noise, then the Bayesian models can sort of ignore your points that are kind of farther away from the rest of the distribution. It can kind of, I'm anthropomorphizing, but the Bayesian model's basically saying, hey, I think that's an outlier. I'm not going to pay as much attention to it. So it's a very cool concept, but basically intractable for real problems. So I don't think it's worth spending too much time talking about this.
I would like to add something to it.
Please.
Mathematics is beautiful. I agree with it. The thing is, though, that the approach is created for infinitely differentiated functions. Even these are some kind of families of the distributions. I look them up, and they all infinitely differentiable. And it is a big, by the way, drawback, because you cannot approach each function with infinitely differentiable function. It's again just pure mathematics. To approach any function in mathematics, they actually use step functions, which are not only not infinitely differentiable, but they have discontinuities at many points. And in general, they can have discontinuous at accountably many points. So, well, infinite anyway. So I always have, my reservations when I see beautiful formulas and I see under them that the author uses infinitely differentiable distributions.
Yeah, no, that's a great point. I always like it when we build something and we're like, wow, this works, like CNNs, they work, when the theoreticians can come in and they can try and understand it and they can explain, certain things. But yes, I don't personally, just simply go by only what, mathematically people have shown. I do think that the experimentalists are still, ahead of the theoreticians on what works. All right, two more topics. So the first just talks about, gosh, I don't even know if this is really regularization, but certainly how do you help your model, um, how do you get a better model? How do you have a smaller gap between your training and your test performance, right? So one technique that we're all familiar with is transfer learning. So I don't know if this picture really explains it, but basically you can have a model that's pre-trained on one task. They show segmentation. For ImageNet, it could be classification, whatever. But many layers of your model have been pre-trained by a large amount of data available for this top task. And then you say, I have my specific task that I want. And so in this case, it's depth estimation. I don't have a lot of data for this. If I only trained my model on the little bit of data I did have, I wouldn't get a very good model. So I'm using this transfer learning to get a better model. You could even have two models that are trained on sort of the same general task, but different, right? A language model trained on general language, and then your model trained specifically on your company's data, your specific application. It's still words, but it's technically, right, a different data distribution. Another example they give is multitask learning. So what if I built my model just to do depth prediction? If I don't have a lot of data, then maybe I'm going to get a not very good model. But if I can also give it good labels for some other task, like segmentation, then maybe because I have more labels contributing to the loss, then my parameters will be better in this case. I'm sure there must be people who do this, but this is certainly not something I see too common. And then another technique, which we'll see more of, but this idea of self-supervised learning. So if you have a certain amount of data and you remove information from your existing data, then it is easy enough to get your model to say, let me make a prediction about information that you removed, and then you now have ground truth labels because you're the one who actually removed it. So like in an image like this, it might be very hard. You'd have to pay people to annotate to say, this is a car, that's a license plate, that's a car, that's a house. But if you just simply remove a rectangular patch and say, hey, predict the pixels that were there, that's something that you can do and you don't have to pay humans to label things. So those are a couple other techniques mentioned in the chapter. And I apologize, my mouse keeps double clicking. The last one, data augmentation. I did jump the gun, so this is here. So here are some very common augmentations. You guys are familiar. There's the albumentations library for Python. So here's your original image. You can do a left-right flip. It's not that obvious that this is cropped, but this is a little bit closer. And I think this is a small rotation. This is like a 10-degree rotation. This is not like huge. Here we've got stretch, we've switched the colors, we've done a little bit of blurring. I don't know what vignette and pin cushion are exactly, but again, there's just different ways you can slightly modify the image. Some of them are lossy, some of them are less lossy. You can even do things, more radical things like, cut mix. We'll take two different images and blend them and then set the label to be a blend of the labels. When I first heard about that, I thought, wow, that's kind of a crazy augmentation, but it does seem to work. And so Ryan mentioned earlier, small data sets, especially for images, it's very clear how you can do image augmentations. People do stuff with like text, and generally speaking, I don't think it has worked as well because like replacing synonyms or dropping letters, it's just not quite the same thing as image augmentations. So here's the final slide for the chapter. It's kind of talks about like 4 broad categories. Okay, so there are things you do that increase the amount of data you have to train on. There are things that you do with the explicit goal of trying to make the function predicted smoother. There are things you do that combine multiple models, and you could argue that the Bayesian and the dropout every time you drop out certain ones, it's like a slightly different model, right? You're not keeping track of them, but it is in that sense. And then the things that find wider minima and then there's overlap between like these different concepts. But so here's a little bit of a Venn diagram that kind of shows you the different thematic things that the different techniques that we talked about, what they're doing. All right. So that's our chapter 9. Any final thoughts, comments, questions?
Great overview, Ted and Ryan. Can I ask you a question back on the Bayesian approach?
Yeah.
So you mentioned intractable, and I understand because you're basically trying to have now, instead of one set of hyperparameters, right? You want to have a distribution of them. So the simplest way that maybe we have been exposed to that is through some kind of grid search, where you try different hyperparameters, you get a loss function, you get a accuracy score, let's say whatever that might be, or your metric, and you note it down, and you notice, okay, for this combination of hyperparameters, I have better performance. Would Bayesian approach need a continuous kind of space, or would simple grid search but applied, over multiple efforts, multiple times, kind of give you an estimate of that Bayesian approach?
I'll give you my answer. I'm not the strongest here. So you mentioned, yes, people do Bayesian search for the best hyperparameters. This chapter was really talking about Bayesian optimization for your model parameters, not your hyperparameters. It's the exact same concept, right? You've got some things that you can change, and you're just trying to find, like, good ones, right? It's just that the number of model parameters is also often orders of magnitude more than the number of hyperparameters you have. So you can just imagine how much more intractable the computation is. GPT-2, if it's considered really tiny by these days, and it had what, 175 million parameters? That's 175 million probability distributions that combine in complex ways. It's intractable to try to compute the actual like full probability distribution and apply Bayes' rule to that.
Yeah, I agree with you. No, I wasn't thinking about the model parameters. I was thinking about the hyperparameters. Okay.
Yeah. So that's actually a separate topic. There's a number of techniques, right? There's genetic techniques. There's even random search techniques for finding optimal hyperparameters. And the problem there is that, again, if you think that your hyperparameter space is not very smooth, that it's very uneven, then just because, I tried 1, 2, 5, 10, and it kept getting worse, doesn't mean for sure that all of a sudden at 20, it might be a lot better. So you're really, really going to have a hard time there.
Yeah. Cool. Thank you.
Thanks.
I want to add
Question.
one more thing here.
Yeah, go ahead, Hakan.
Oh, thank you. So one thing we didn't mention, the in decision trees kind of approaches XGBoost like GBM. In those methods, I see that people use both. There are this regularization functions, like the gain. When they calculate the gain, they put this the same idea like in last. So they put this penalty. On top of that, we also limit the number of leaves that a tree can have, or the depth of the tree. That way you can use simple trees to make decisions. That way you can also prevent the overfit or regularize.
Yeah, that's a good point. Like, I don't know that there's a great neural network analogy for limiting the height of trees or something like that. The ones that you do use, like restricting the number of inputs that you can use for like a given split, I think of that as being somewhat analogous to dropout. So if you say I have 100 inputs and I will only let you use 10 at a time, that's a little bit like 90% dropout.
Yeah.
But yeah, some of the other ones don't necessarily have a good intuition for how it compares to deep learning. But again, I think it might sort of relate to these different ideas of like smaller trees makes the function smoother, and you're summing up a lot of small smooth functions, and so that's the idea here.
General idea, using less parameters, make it simpler, right?
Yeah, make it simpler. Yeah. Someone has a good correction in the chat for me. So it says, he asked, isn't what you mentioned mix up, cut mix, mixes portions of image with other portions or noise? I forget the exact definition. If you just take 30% one image, 70% another image, and that's what you use to train on, and you use the labels of 0.3 and 0.7, that's correct. That's mix up. Ryan, can you help me out here? I don't remember exactly the definition of cut mix. Is it also using cropping in addition to? I think it's mix up, but with crops, not full images.
Not sure. I've used both, but I don't remember exactly which is which.
Yeah, but it's a good point. I apologize. I may not have been precise. I may have misspoken. But definitely, like, look at the album mutations library. There's lots and lots of different options, and I did want to mention those just because like mix up and cut mix are pretty popular. They're pretty common. So I apologize though if I got the exact definition slightly off. Cool. There's the link.
Can I ask one more question, Ted?
Yeah.
So you mentioned these techniques, and we've used them, many of them, especially in computer vision. So what about in the NLP world? Which ones are most popular in your opinion, and which ones maybe are not covered here?
So let's see here. I don't see dropout as much. I still do see, gosh, it's not really in the slides. But basically, penalizing weights. So that still seems to be a fairly common technique. And anytime you see somebody say, I used Atom W instead of Atom, that means that basically there is like an L2 weight penalty. And so Atom W has an extra parameter, which is like that lambda. How strong do you want to penalize the weights? Still see that a lot in deep learning. Applying noise and not so much for LLMs. Then the stuff like transfer learning. Again, multitask learning is hard. You saw that in BERT, you had these two tasks. You had mass language modeling and you had next sentence prediction. I think there have been papers that have come out that said that the next sentence prediction contributed like less than 1% towards the end result, and that if you had trained BERT on just the mass language modeling, you get almost the exact same thing. So I think it's really hard to have a multitask, multiple losses that meaningfully contribute. Oh yeah, great. So in the chat, stochastic weight averaging, yeah, this is getting super popular. There's in the chapter, I think they talked about, hey, I just did a simple training of a model, and then maybe at the end, I'm going to take my final weights. I'll take the weights from, whatever, 1,000 steps before that, and I'll take a model from 5,000 steps before that, and I'll average the three of them or something like that. But another thing that people do is, instead of doing the regular gradient update, you do a modified update where it's usually it's like an exponential moving average, but it's basically an average of your current gradient plus some of your past gradients. And this basically will do smoothing of your gradient. So hypothetically, if you had gradients that went like doink, 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 they're all going up, but they're going left and right, then this stochastic weight averaging is going to sort of average them together and get you to go more straight up and less left and right. And there's some other properties of it that I think are a little bit more technical. Is that technically a regularization technique? I'm not even sure. Again, like I'm not sure what the definition is, but in order to get a better model, that seems to be a very common thing. Question in the chat: does momentum account for that? Yes, and this people use on top of even momentum, and I think there's some more complex statistical reasons why this is a principled thing to do, but I'm not sure that I remember enough to be able to articulate those exactly. But this is not mutually exclusive. People will use atom with momentum and use stochastic weight averaging. That's a great call out. Thanks for putting that in the chat.
I want to add one more thing. So I read one article once. It was about label smoothing. Instead of assigning in the classification problem, instead of assigning 0, 1 to classes, they are assigning this probability of being cat or dog. So it says if it is greater than 0.9, you can call it cat. So the labels are like probabilities for classes, and that way it's they create this imperfect labeling, and then that adds noise to the data, and then so that way the model doesn't overfit to the data. That I wanted to mention that too.
Awesome. Yeah, I believe the chapter mentioned it, but it didn't really get captured in the slide. The chapter says there's 3 ways you can add noise. You can add noise to your training examples. You can add noise to your weights throughout the training process. And you might argue that stochastic weight averaging is a way of adding noise to the weights. And then the other thing you do is you can add noise to your labels. And so instead of saying, even though you're training on an image and you know it's a cat, or rather, if the ground truth label says this is a cat, you might just train it with a 0.9 instead of 1.0, and then that will give you slightly different problems, and it can avoid some of the overconfidently wrong predictions that your model will make. It also accounts for the fact that in most training sets, there's stuff that's the labels aren't great, either because occasionally you have flat out human error, you have mistaken labels, but then like imagine ImageNet, you have a class called B, and there's this picture of this beautiful flower and there's a bee on it. It's like, what's to say that this isn't like a flower, that this is a bee, right? So even though the label's not in that case flat out wrong, it's not clear that you can say that this picture should really conceptually be considered 100% B, 0% everything else. So yeah, label smoothing gets used for all those reasons.
Thank you.
Anything else? All right, thanks guys. I appreciate the input. It's much nicer when it's a little bit more of an interactive discussion. And also thank you for all the people who mentioned other things that either I dropped out or wasn't covered in the chapter. Yeah, I mean, regularization, it's a big deal because everyone wants the best models, and just very simple, naive training, especially if you have small data, is generally not going to get you there. All right, I think we'll end things here and we'll shift gears to the office hours session.